mentioned partnership between Warwick University of Warwick in UK, IIT Kharagpur, IIT BHU, and Simulonics is the industry partner. The idea is to do the basically focus on the sustainable mobility and battery space, looking at translation research and capability building. The overall intention is to develop the collaborative partnership between UK and India, between academia and industry, to improve to have the skill development in India as well as UK. So we had three webinars before this one. The first three basically focused on the sustainability, micromobility, then sustainability within micromobility, and then data analytics, especially looking at the batteries. This fourth webinar is looking at AI and battery, the cusp of AI and energy. And that's the one of the critical challenges emerging for this decade. The idea would be to understand from the industry what are the challenges, how AI can solve some of those challenges, what are the tools that are being developed by industry and academia to support the industry to solve these challenges, and what are the current limitations in terms of AI development. We have three eminent speakers here. Dr. Kutubuddin from Envision Energy as the CTO at Envision. Dr. Prashant Srivastava from Urja Energy, and Dr. Mona, I think I missed the name here, but Dr. Mona Neri from University of Warwick. So that's the line of speakers. I think I'll stop here and I'll let Kutub to take the stage. The flow of the webinar would be Dr. Kutub will start talking about industry perspective. We'll then go to Dr. Prashant talking about Urja's experience in terms of battery modeling, role of AIML, and then we'll go to Dr. Mona talking about academic understanding of various challenges in battery applications as well as manufacturing. Lastly, I will present Simulonics' work. To you, Dr. Kutub. Thanks.
Okay, thank you, Rutuj, and welcome everybody. It's my absolute pleasure to be presenting today. What I will do is just start talking very highly at the beginning around AI and the use of AI today in our business. And our business, obviously, Envision Energy covers a lot of things. I'll focus on specifically on batteries and how we use AI today for batteries. And then I'll start to talk a little bit about how we can apply that to micromobility. So what you're seeing on the screen, just going through some of the examples of where we use AI. On the left side, you're seeing AI being used for new material composition. So we are obviously Envision, and then we have AESC, which is our business that makes cells. Typically, when we investigate new materials, we go through this trial and error, right? You change the material a little bit, then you see what's the impact, and you continuously evolve your technology or your material science like this, making some change, looking at the impact, and then going through that route and over again. This is very costly and very, in terms of resources, but of course also time. What we're doing now is using AI to quickly investigate how we can improve materials for lifetime, improve for safety, and improve even for cost. Okay, and this is now the turnaround time for development of new materials has reduced dramatically. The second one that you see there, oops. Let's go back. The second one that you see there in the middle is this is keep on moving. Hold on. Is the manufacturing. So in gigafactory manufacturing, we also there's a closed loop system, and what you can do is you use AI not just to capture information, but you have real-time inspection. We've worked out some fascinating results of how using AI, how factors in the factory can affect your manufacturing yield, your defects, and other things. At the end, what you can do is use AI to not just identify but to rectify this. This increases our yields, this reduces our defects, and you end up with products that are better for warranty and last longer. And of course, there's continuous learning there. The third picture that you see here, this is now when you start to take the cell and build the system. And when you're building the system, the one that you actually see there is a graph neural network that we're using. And graph neural networks are very good at capturing geometry. And what you're doing, what you're seeing there is a grid scale battery that is going through a thermal simulation. So we moved away from CFD to start to use AI. And you're going to see a lot of this now. Moving away from traditional methods like CFD and CAE to go into using AI to do this. And the final one that you see here is more around the power electronics. Now, these are just some aspects of where we can use batteries in the design phase. But after a battery is designed and it's deployed into the field, you want to also use AI. And this is the next picture here. What we're doing is actually using AI for battery health and safety. We can use it for diagnostics and we can use it for prognostics. This is a particular example, and I don't want to go into it in detail. This is published, so you can check our names, and you will find this on published in, I think, scientific reports, and there's another one on a few journals. But we've published most of our research. But here, for example, what we're doing is using contrastive learning, a particular methodology or in data science or AI, to predict battery health. Normally, you do a time series forecast where you say, look, you've got some input data, and then you predict then what the output is. Here, we sort of flip the idea on its head. We ask the question, given this usage data and a million simulated worlds, what does this data closely match in terms of your simulated worlds? And this is how you make predictions, and it worked very well. But the point here is that prognostics and diagnostics is what we're doing here. Now let's connect this to the micromobility. Excuse me. Micromobility, and I'm thinking now about the scooters, the bikes, things like this. This is actually characterized by harsher usage profiles. What I mean is that typically you see the depth of discharge of application is very large. And I think myself and Rutuj wrote a paper a couple of years ago actually on the impact of DOD on degradation. So you can refer to that about how detrimental DOD is. So you've got large DOD. It's characterized by more cycles, right? So typically a car maybe uses only 20-30% maximum of its SOC per day. In micromobility, you could be using up to 70 to even 100 or even more than one cycle per day, right? So you've got large cycling. You've got higher transients. So these things, people on the scooters, they go up hills, down hills. So you get much more variance in the transient or the C rate behavior. This is how it's characterized. It's a very, very harsh way of using a battery. And at the same time, if you look at the business models that are prevalent now, a lot of these micromobility applications are using a business model that is battery swapping, right? So now this means there are fleet operators, and fleet operators want minimum downtime. They also want to manage their infrastructure and their cost. They want to improve their fleet utilization. So this is where diagnostics and prognostics can help. It helps in fleet utilization, it helps in managing safety, helps in battery replacement optimization, and just having strategic insights. And I believe also what you can do with AI and analytics is open up new business models. And I give you an example. Today, for example, if in the UK, if you insure a car, they can lower your insurance premium by putting a black box on your car. This just measures how you're driving, right? And if you're driving very good, they reduce your insurance premiums. You can imagine this now being applied even to micromobility, for example, where by you behaving or being less aggressive with the transport or the equipment, you might get some sort of premium. Or even understanding how, like if you were leasing a battery, for example, how should the one who's producing this battery charge you? So there are a lot of the analytics can open up a lot more sophisticated and more intelligent business models that maybe even starts to grow this space and makes this space more affordable and more accessible. So this is just a little bit about how we use AI in the field or currently as an OEM, and where we can take some of this AI knowledge and apply it to micromobility. I look forward to some of the questions that come up later. Thank you very much. Thank you.
Thanks a lot, Kutub. I think that's very interesting perspective from industry. I think we will now jump to Dr. Mona from University of Warwick to understand her work on the AI, and especially AI for battery manufacturing as well as applications. Dr. Mona, you can take the stage. Thank you.
Yes, absolutely. Thank you very much for having me. And I'm just going to start by sharing my screen. Please bear with me until I go full screen, and then I'll take it from there. Hopefully you have the right screen now. Okay.
Yes.
Right. Hello, everyone. It's a great pleasure, and thanks, Amrita, and also organizers for the event and having me. And I already see that you have gone through a lot of introductory and also a lot of good topics, but Kutub. So some of these I'm gonna take you through is looking at literally some of those that Kutub mentioned, but from a little bit of academic point of view, probably. I'm going to start by a very short introduction what we do in the battery systems group in WMG. So battery systems group in WMG is made up of 4 academics and also about 30 plus other engineers and postdoctoral researchers, and on top of that about 20 of research PhD students, PGRs, that are looking at different aspects of battery manufacturing, battery performance analysis, degradation, and also looking at the integration of that battery into the powertrain of different applications, including micromobility, EVs, maritime systems, and aerospace systems. So as an institution, we are literally looking at every small element to big element of a battery chain, starting from material synthesis all the way down to the recycling and back to the manufacturing and every challenge that it has in between. So the area that I am mainly covering is battery modeling. That starts from battery manufacturing, process modeling, battery performance modeling, state of charge, state of health, degradation modeling, and also dealing with the second life batteries across different applications. So as it's going to be a fairly short talk, what I'm going to do is probably start with a bigger picture of the sort of challenges that we face in, and then I'm going to put that into the context of where exactly that AI is helping us and how big we can go and where is still the areas that need a little bit of work remaining in that. So if I be to characterize this challenges and to put these challenges into different categories, obviously it starts with the innovation and the design, looking at how we can improve the material for a certain purpose of a battery, for a certain usage, and also the challenges of formulation optimization and making those material work together. Then it comes to how to manufacture that innovative combination or the cell format or the design of the battery that one has in mind, because it is expected to deliver a certain performance, because not everything that is being designed and innovated is manufacturable. So the next challenge in here is looking at how that manufacturing can happen, by which technique and under which category of control factors and processes, how to make it scalable from a handful of cells to literally millions of cells, and also how to make it zero defect or minimum defect manufacturing. The next area is the operational challenges that we're facing, which is looking at the battery when it's being used inside the applications, and the fact that its state of charge needs to be estimated, its degradation needs to be monitored, its safety and balancing performance needs to be dealt with, and also its thermal behavior needs to be monitored. And also, on top of this, we have the maintenance of those batteries, which usually sometimes we refer to that as a degradation, warranty, lifetime monitoring and control. And also then it takes us to the reuse and repurpose and recycle. And each of these gray areas, if you look at it, there are a lot of challenges that is a combination of limited understanding based on the physics that usually has been around for probably half a decade now. And also the challenge that we are dealing with a lot of data in here, but not necessarily enough quality data for that is suitable for understanding. And sometimes we are dealing with a lot of missing values, noisy measurements that are coming in millions. So that makes the life a little bit also difficult. So these gray areas are the areas that we already have some sort of understanding, but the understanding that comes from the scientific background is not being sufficient. So this is exactly when we refer to how AI is improving the battery industry. So this is the bigger picture. This is literally every element in here is benefiting from AI, from material discovery by looking at the microstructure development, the formulation optimization, the optimization problem itself to run at higher scale, and some of these blocks that I'm going to take you through in the next slide. So basically, every area that we are dealing with the batteries today is benefiting AI because the limited physics-based or mechanistic understanding behind them. But what we exactly mean about AI in the energy storage context is literally every technology out there is now very much applicable to the battery industry. Is if I probably was going to have this talk probably about 5 years ago, there was a little just probably this graph very limited that showed, okay, we have machine learning here and we're using that to analyze our data, to extract some insight from it, and also to achieve some predictability. But right now, if I look at all the existing, as not, and I would agree that some might have different names and people call these different things, but literally now we're moving to a stage that every technology out there can be used in the energy storage because they are very well developed now. And also we right now have a better understanding of the challenges of the energy storage area and how that could map to some of these tools. So some of these that have been around for probably ages, for tens of years, some are still a little bit newer, and there is a very much and very good scope of applying this. So this particularly when I say I'm looking at this from the academic and research and a little bit lower TRL point of view, is that some of these is very much adaptable, very much usable, and you have seen some examples. I'm going to show you some examples, but some of these are exactly at the beginning of the journey, how we can capture all the information from the domain and map it to the existing models so it can also benefit our energy storage area. So I'm going to keep this focus still at the two circles at the middle, which is deep learning and machine learning, and I'm going to take you through how actually AI is being used for that middle block of my first slide, which is the operation challenge. So the operation challenge is that we're looking at maintaining battery, we're looking at understanding the battery while it is being used in a single application. And obviously, you would agree that this is partly coming by the battery management system and the fact that we need to have an understanding of the system, which is also runnable in limited capability of the processing unit of the application. And this is exactly the battery management units, battery management systems unit challenges come to mind. And the fact that you need to capture that data, process that data efficiently enough and compact enough that is real time also runnable. So what are the challenges that AI is supporting here? is actually that real-time implementation of the state of charge and a state of health. Probably I'm going to keep a state of health for the next and the other slides, but here a state of charge and also a state of energy and function is the thing that AI is literally helping a lot. The other bit is achieving high fidelity models, which are not mainly and directly for battery management system, but are a good backbone of developing good batteries, because it is just by having this predictability through high fidelity models we can design and come back to the manufacturing phase, to the innovation phase, and also deal with the challenges that certain applications have with. So developing these high fidelity models, which are normally based on physics, if they remain only based on physics, could be really challenging, because obviously there are some very difficult to understand phenomena in them, which can be very complementary and well understood, but even though I'm saying black boxes of AI. So there are some examples here. If there is a sample high fidelity, these are some famous models here, DFM models, SPME models, and etc. These have a lot of parameters, and even though we can experimentally find some of these parameters by opening up, tearing up the cell, but still maintaining them over time needs a lot of data that can just be measured from the surface of the battery while the battery is in operation, and making that model work over time needs to have constant adaptation and constant improvement that can only happen by data and in a data-driven mechanism. So this is one example that AI is actually supporting the battery management system and performance. The next one is degradation. And degradation is about looking at how the battery capacity changes, capacity or equivalent to that internal resistance or other definitions of battery health changes over time. And this actually depends on how the battery is being used, and Kudo mentioned that very nicely in the context of micromobility system, and this is exactly one of the challenges that we face when the battery is being used in different areas, the maritime, aerospace, micromobility. They face different usage scenarios, different challenges, different depths of discharge, different status of different main windows of a state of charge, which is actually one of the key elements of battery degradation and its definition. So this is exactly the point that we are dealing with a lot of uncertainty that are very difficult to be understood by just physics-based model. And this is exactly what we have also a lot of data, but not necessarily complete data. So one of the challenges that we face, for example, in micromobility systems is the large number of the fleet that the data from them can be recorded, but probably not to the same quality as you would recording that data from an EV or from an aircraft. And so there is a lot of missing information, and we are dealing with the smaller battery packs that you cannot deal with a lot of errors in them. So in here, we're dealing with large volumes of data that need to characterize not only calendar aging, which is when you just park your vehicle and you just not use it, but also cycle aging depending on how you use it. And one of the roles of AI in here is exactly to categorize different users into different type of behaviors and then link that to how their battery in their vehicle will degrade. One of the other bits and challenges that we face in here is the constant innovation in the battery, the change in the design, the change in the chemistries and also form factors and everything that makes the life again a lot harder, because even though we have these models working in a certain boundary and circumstances for chemistries, for different use cases, it is not yet applicable to other chemistry and use cases. And this makes it a lot harder for any AI models, leave alone those that were just based on physics, to work in that area. And this is exactly where something like transfer learning comes actually very handy, and it gives you an initial point for training these models so that not everything has to start from scratch. So this is the second area that I wanted to discuss in that box of operation. And finally, the last one. So this degradation is very challenging, but because as we move forward, as I just mentioned, there are millions and millions of data points being collected over time, and also there are the challenge of moving this data and communicating this data with servers, maintaining them, with the cloud processing, and also feeding back that information to each single element of the fleet as a fleet manager or the owner. So what happens in practice is that the models cannot really, even though we have them based on the previous slide, working quite nicely based on a certain volume of the data and in a certain time window and maintained even well over time, because this area is very wide depending on how you drive your vehicle, where you store it, how much you left it to be charged, do you fully charge it at one window at depth of discharge, you stop using it, and it's very much different from one user to another, and we're talking about billions of probably users around the world. What naturally happens that the fleet managers naturally somehow average all of these information, even though they have very much accurate models and very good working models, and then communicate back that. So basically, if I'm a very gentle driver, I receive same prediction almost with the one that is using their vehicle every day in very harsh environment. And this is what we want to avoid as we move forward. And this is what exactly one of those areas very much interested for us. And also we are working on that, moving to what we call decentralized degradation. And this is exactly where one of those AI models that we say move, one of those methodologies that helps us to move from a centralized cloud-based calculation to decentralize edge to cloud based calculation can be really useful. But the challenge in here is that here these models need to be trained based on individual or a cluster of clients, we would say. And the data is much more limited compared to when you mix all of these data together. So these models need to perform quite nicely in an individual cluster, but also need to be able, with a mechanism of aggregation, communicate with the others. One of the advantages in here is also for those that have regional fleet managements, and AI has been actually probably the only solution in here, because you can capture the data, you can characterize and categorize this data based on different regions that are being used, if not to go into the individual level of clients. And these are all based on the category of decentralized learning that facilitates such things. And finally, the last one is about the maintenance. And this, when we move to the second life, so one of the challenges of, again, micromobility systems is that because these are smaller batteries being used in probably on a daily basis, and also are being used in probably harsher charge and discharge conditions rather than EVs, and also obviously larger systems, there are a lot of these small batteries that need to be dealt with as we move forward to the second life application of them. And this is exactly where we are dealing with a lot of data that need to be used to understand the remaining, let's say, literally the remaining life of the second life batteries, and the fact that there are actually could be much left in them. In micromobility, this is still a challenge. There is still not very good answer around it. In larger battery packs, the question is how to regroup them, how to sort them, and how to reuse them. So this is also another area that we are facing, dealing with a lot of data out there that obviously, without having a concise and also understandable AI algorithm, these are not practical and not doable. And eventually, the challenges that are still remaining out there is that it is not just about having these techniques working on a bunch of data, on a small data. But the main challenge in here is that making it work on very sparse data, very segregated data, and also data that are coming from different sources. They are hard to aggregate, and also the challenge that you need to communicate this to the user, and the user sometimes is just you sitting at your vehicle and driving, but also sometimes it's the fleet manager, the manufacturer that need to have some insights about how these batteries are being used. So basically, the challenge in here is not just technical, but it's also social, and also about explaining the results. And this is also an area that is very much of interest for my group. And we're looking at how to interpret what you get out of some of these complex models that is applicable to everyone that is interested in these battery systems. Thanks for listening, and happy to take questions.
Thanks a lot, Dr. Mona. I think this is a very, very deep and interesting presentation. Good to see the flow from Kutub's industrial problems to the solutions that you're working on the academic side, the connection. Unfortunately, we don't have Dr. Prashant from Urja, so we'll skip that presentation and I'll directly come to my presentation, where I will talk about some of the challenges that I see in the industry and what we are doing around it. So yeah, so we are Symbionics. We are basically a battery intelligence company. We are looking into.
Rutuj,
Yeah.
sorry to disturb. Yeah, I guess your screen is not fully visible.
Is it better, or is
Now it's we can see the presentation mode, but the slides we can see, but not in the presentation mode.
are you able to see it now?
As
No?
soon as you put the presentation,
Oh, there is
we get
something.
like click to exit. Are you using two
Okay.
screens?
Let me stop and try it again. Okay, give me a second.
Yeah, sure.
Is it visible
Yeah,
now?
much better. Perfect. Perfect.
Okay.
Yeah, please
Cool,
go ahead.
cool.
Thank you.
Yeah. So yeah, again, I'm Dr. Rutuj Deshpande, the CEO of Symbionics, and we are into battery intelligence. The idea is to unlock the full potential of battery through physics-informed AI and advanced algorithms. We work with various customers, and the challenges we are seeing is, especially as the battery industry is growing, we see a lot of EV recalls, and the cost is growing. The BESS downtime, like what Kutub mentioned during his presentation, is one of the biggest challenges with BESS systems, where the large energy storage operators are promising that they can deliver or they can accept certain energy, but suddenly the battery is not reliable anymore. There are warranty risks when, as you use the battery over life, the batteries are degrading sometimes faster than what they were expected. Then the safety regulations are getting tighter, and we see a lot of field failures overall. And um, the challenges with batteries, these are complex problems. The battery itself is a complex chemistry, physics, and a system altogether. And especially the inconsistency of battery life and performance is one of the key challenges that we are seeing from various clients that we are working with. In addition to that, there is of course a safety risk. We are talking about large energy being stored in a small volume, and there is also a kind of absence of good interpretation of the data. So intelligent interpretation of data is where is what is needed for this field. I'll give a few examples of some of the problems that our customers are facing. For example, one of our customers, basically, he said they have a vehicle, shows certain state of charge of 80% and certain miles left to, for example, to 80 miles, and the user drives a bit, and suddenly the number of miles drop to 160. The state of charge dropped to 50%. So you may not drive the same amount to really same amount of energy, but still there is sudden change in the state of charge estimation as well as the miles to empty estimation. Similar problem is observed in the energy storage systems where the energy storage operators, uh, one of our clients came to us saying that I have this 1 megawatt hour of system, but I can get only zero 0.9 megawatt hours reliably. So I may not get 1 megawatt hour each time. And these kind of problems, there are multiple reasons why this could happen. For example, simple things like state of charge estimation. Now, this problem has been dealt for years. There are a lot of algorithms which deal with state of charge estimation, like Coulomb counting, amp hour integration, various Kalman filters. Yet, estimating state of charge is still a big problem, especially for LFP chemistry, where the voltage curves are very flat. Um, Similarly, state of health estimation is a problem. We'll take a look at one of the examples. Another important problem that this battery industry faces is the lack of understanding of state of charge imbalance. Especially in the LFP chemistry, lithium iron phosphate, the voltage curve is so flat that you really don't know whether you're at 50% or 80% state of charge, because there is no difference in the voltage response of the battery. And that may lead to state of charge imbalance. So some of your cells are sitting at low state of charge and some are sitting at high state of charge. And you think you have certain state of charge of the overall battery, but the weakest link of the entire battery will govern what's the energy available. Similarly, lack of detection of weakest cell, um, wrong state of energy estimation. So all of these could cause the problem of why my range is suddenly dropping much faster than what I was expecting, or why my battery is not giving me the same energy that it promised me to give on day one. The other set of problems is why my batteries degrade so quickly. So one of the OEMs we are working with had a really good battery from a good cell level vendor. So the cell level battery health during cell level testing was really good. But when they put it on the field, they saw that the batteries were degrading much faster. Now, this year two is just an example, but it was much faster than what they were expecting. So the new battery to degraded battery did not take as much time as it was expected. Um, and again, the challenges could be the quality of cells. How are the cell quality checks are being done? What kind of data being passed through? What kind of cell sorting is being done? The other could be bad controls. If they have good cells, good packs, if the controls are not good in terms of current limits, temperature limits, voltage limits, then you can have batteries degrading faster. Or one of the biggest problem is incorrect understanding of usage. So you are designing for a certain average user, whereas you don't have exact understanding of your usage being done. And I think Dr. Mona talked about it. You have users in hot environment, cold environment, maybe two-wheeler, three-wheeler, or even car users using in Phoenix, Arizona versus, let's say, Michigan, or in India here in Pune versus, let's say, Shimla. So you could have varied temperature conditions, the depth of discharge conditions, and how all of those will affect the degradation rate is kind of not understood. So when they are designing the system, a lack of good data of usage and then using that data to build the design of the battery pack is missing. Or even wrong cell selection could be another challenge, right? You may think that this cell is good based on certain standard cycling conditions. Now, when you take those standard conditions and put it on field where every user is different, some users are doing fast charge every day versus some are doing a longer depth of discharge and stuff. Your life performance could be very different than what you have understood. The third set of problems is one of the customers basically came to us and asked us, okay, how much energy do I have today? Now, if you think about energy calculation, it could be very simple that if I can integrate amp hours in a certain state of charge window, you can calculate what's the capacity available today. the formula looks simple, but when he did that and calculated state of health, he found that over years he gets points all over the place. And I'm sure Kutub has seen these kind of plots that the state of health being calculated on these large BESS systems um, could go anywhere, and it can actually a lot of times it goes above 100% if you are using a simple formula. Now, this is a problem of plenty. I mean, you have a lot of data, but then if you try to use any ML model or black box model, you can actually fit a line or whatever curve through all of this data, and it will still have same R square value. So, so you can, any ML model can fit or cannot fit with this kind of data. So that means you have to have clarity on what kind of measurement errors you're looking at, and just pure data driven models may not work every time. You need to have understanding of physics to really parse out what is the real data, what is the garbage data in such cases. So in Simulonics, we basically start with physics and then we couple it with AI. So it's not completely black box solution. So we couple the battery physics with the AI, and then we develop controls on board for the vehicle, so that whatever solution we are developing, it's not applicable only for the beginning of life, but it's applicable throughout. So we are constantly learning as we go through on BMS or through digital twin, and we are also using this to customize the design of the battery for a specific of our customers. Uh, we are serving various industries, batteries being core of all these industries: electric vehicle, energy storage, aerospace, battery manufacturers, as well as portable electronics. Few examples I can give is like for one of our clients, we could increase their warranty was 150,000 miles, the battery to degrade to 80%, but we could increase it to 300 plus thousand miles through design changes, control changes at the cell level and at the pack level. We could for one customer, we could save millions of dollars by just estimating the SOC imbalance on a LFP cell, because again, with the flat voltage curve, it's very difficult to do that with pure data. So we couple data with physics to do that. We could decrease the fast charging time from 37 minutes to 25 minutes for another customer. And for one customer, we could save the initial battery cost significantly by optimizing the battery design. So overall, we are working on all of these problems, coupling the battery physics with the data, and that's where I will stop. Cool. So I think we went through different segments and different ideas. We have 10 to 15 minutes left, so we'll have quick few questions to the panelists from my side, and then we can open it for the floor. Starting with Kutub, I think you talked about AI usage for your application, especially the battery manufacturing, as well as a bit of energy storage and mobility. What do you think? Like there are both views on AI. Some people say AI can solve everything. The other people say it's just another tool, right? What's your take on AI? Where it's most useful, and what do you think is the future there?
Okay, so I mean, you can't stuff AI into everything. And on practical terms, really, we are seeing genuine benefits from AI, not just, by the way, just batteries, but even as a business, right? How we use AI. So even I have a team that does NDAs with AI now, right? So they will just you will just put an NDA comes in, you stick it into an AI tool, and it will just flag all the problems. So it's being used as a way to be more efficient. I don't think it replaces everything, because the reality is at the end, the lawyer still has to read that contract and still say, okay, there's still flags there. But certainly the way we've applied AI to make the business more efficient has been quite amazing over the last couple of years. Now, going back to batteries specifically, again, all problems aren't AI. Like, for example, some of the problems might just be a sensor issue, right? So, for example, you want to know if a cell is hot. For example, you've got a loose connection, all right? You've got in a pack, let's imagine one of your welds isn't properly done. Now, that's going to increase the resistance and that's going to get really hot. That's not really an AI problem, right? Your BMS or your SCADA system will pick up that there's something wrong, but that actually fundamentally is a sensor thing. So a sensor will pick it up. But I think AI is unlocking a lot of value really beyond just engineering. Is going into the space of warranties, is going into the space of uh, business models, as I said before. Even obviously on the energy storage side, you can start to use AI for trading. Again, not exactly batteries, but if you think about it, one of the big problems that we need to solve is the stability of the grid, right? And when you're talking about the stability of the grid, things like grid forming comes into question. Then the grid forming then starts to say, what grid am I connected to? Is a fundamental issue of how the PCS works. And this is measured by maybe your SCR level or let's just say how weak or strong your grid is. Inside the control loop now, you can have AI. So you can take data from multiple projects that you have in a country or a jurisdiction, take nodal data, put it inside, and then try to answer that question: what type of grid am I connected to? And that then feeds back into your control loop. So there are very, very advanced applications going, and even you mentioned about BMS and car, but if you look at the edge computing, let's say you have a very heavy model, right? You're going to still use stuff on the cloud. You'll send data back onto the cloud, reparameterize, and then use edge computing to send back the updates of parameters, right? But and this is used in the electric vehicle space. So there are spaces and advances that AI is bringing that that is revolutionary. But again, it doesn't fit all problems, right? It doesn't fit all problems. Okay.
Perfect. Thank you. Yeah, it's a great answer. So yeah, taking the train of thoughts towards your experience, Mona, uh, like you mentioned good data and bad data, right? And you also mentioned about, and then the other question becomes like translating academic research um, to the industrial problems, right? So two questions for you, like what's your experience with the data that's coming to you? Of course, typically academics tend to be data pass. I mean, you may or may not have enough data, and that's how are you dealing with that? And secondly, what translation do you see towards the industry?
So in terms of data, that's actually a very good question. So literally the data is the main input to the AI, because the rest of it is the fundamentals based on calculus, algebra, and those algorithms that we have had around for many years. So the bottleneck here is really the data. And when we say good data and bad data, we are referring to the data that is right now. One of the challenging bits is that because there is capability to record the data in high volumes, there is expectation that, okay, because it's large, it's then good. But that's not the case, unfortunately, in every scenario. So we are measuring data, but sometimes the data is not being recorded in right resolution. Sometimes, as was just mentioned, it's not being recorded in the right accuracy, and it's not repeatable. So even though there is data, large volumes of data in some areas, they're not still very much useful, and we are still dealing with a lot of noisy data, a lot of sparse data, the data that particularly do not follow a certain standard, and therefore there is a lot of data pre-processing and data processing elements involved before it can be used for any AI and development. So data is actually one of the challenges here. So the particular challenge that probably battery industry faces is that lack of standardized way of recording this data. Starting from the manufacturing processes, each manufacturer is just recording the data that they are interested in without having that in mind, that how this is going to be used later by anybody else. And of course, that's part of their business confidentiality and everything. But this is also the challenge we face in the research environment. So those that are measuring the resolution, the methods that I'm using in our battery manufacturing, for example, a scale-up line, is not at all similar to someone else doing that. And this makes the transferability also a challenge. So not only the quality of those AI models remain very difficult to be maintained from one case to another, but also from one scale to another. So yeah, data is a challenge. We need some sort of a standardized way of collecting this data, minimal data pre-processing before things move to the AI, or a very much intelligent system that can process this data before it's being used and flags out things and helps to create the missing points, missing data. And this is particularly very important in the R&D environment. So this is exactly AI itself can be very useful, having a mechanism of defining what data you would need for your AI algorithm is a challenge itself. And in terms of transferability, yes, this transferability is coming in different aspects. Sometimes it's from one scale to another. So something that we are looking at probably tens of batteries, and also, for example, at a coin cell, it is not necessarily transferable to the next scale or to higher number of cases. And this is another challenge for itself. And being able to understand where that exact difference in the data and scenarios coming from and how to embed that and how to code that into an existing model is part of the AI algorithms challenge. Transfer learning being one of them, fine-tuning, retraining, auto-training, and etc. is some of these methodologies to deal with this challenge. But this is mainly still a very much valid challenge, not only from one institution to another in academia, but also from from academia to industry, from one industry to another. So this is still very much algorithmic and data challenge.
Great. Yeah, thanks for that detailed answer. So I think we have a couple of questions on which are posted here. One of them is again probably back to you, Mona, right? Which method is employed to identify parameters? I mean, I think I can talk about it as well, but I don't want to talk because a lot of it is confidential. But maybe you can
So
talk a bit.
do we mean parameters of the AI models, probably?
Correct. Yeah.
Yeah. Okay. So normally, there are different approaches to do this, but probably optimization based on a certain target is the best way for hyperparameter tuning. So one of the challenges of AI models definitely have is from one scenario to another, one case to another. This is exactly the hyperparameters that will change most, and that has a critical effect on the performance. But probably the only thing I can think of that we use is multi-objective optimization. And this is not too bad because this hyperparameter tuning and auto-tuning and optimization normally happens just in the training phase or at the maintenance interval. So we're not too worried about having them running real time in most cases, but this could be this is one of the solutions. The rest is like having an physics informed type of interventions to your neural network or your AI model. So some of those hyperparameters, if you can link them and supposedly train with respect to the physics behind and keep them bounded by that physics, some of them can also, but it's not for all of them. So this could be another complementary approach to deal with that.
Totally. I think that's also close to, I mean, the answer is also related to the third question that was asked, how to transfer real-time model without having data. So I can talk about it. So continuing with the thought that Mona talked about, sometimes you may or may not have enough data, and physics can inform you what can happen. So a lot of times we are using surrogate physics models to train AI, and then use that AI to do predictions for large number of scenarios. If we have good surrogate model, it helps. If we don't have a surrogate model, then it becomes a challenge, right? So how do you couple again with the physics models? The challenge is getting the data. It takes long time, and same challenges with the AI, that you need a lot of data, right? So coupling them to minimize the data need is one of the things that we are working on for some of our clients. One of the practical problems that we are solving is how do we minimize the fast charging development duration. Sometimes it takes years to build a good fast charging profile that will last for 8 to 10 years for the OEM application. And can we reduce it to 4 or 5 months? So yeah, we are using coupling basically physics models to AI. Coming back to you, Kutub, on safety side from the large BSS systems, have you worked on AI to improve overall battery safety?
Yeah,
Yeah.
yeah.
Okay.
So, I mean, look, so we've worked on models. So you can imagine like this. One of the principal, it's not the only, but one of the principal mechanisms that are almost hidden is the growth of lithium dendrites in cells, right? So here you've got two plates, and what's happening is the dendrites growing, it pierces through the separator and causes an internal short circuit. But the reality of it is that this is a very slow process. It's not like a nail going in. It's very, very gradual. And actually, you can start to see signatures inside your voltage profiles, right? So now so what you're trying to do is you are trying, and let's see, from our perspective, we have maybe 30,000 testing channels, right? We spend more than 200 million USD per cell program on just cell level testing. I'm not talking about something else. We create more than 5 terabytes of data for these cell programs every year or something like this. So it's a heavy, we have a lot of data. And so one thing we're lucky is that we're data rich, right? And we're an R&D organization, which also means you can do anything funky. Like, Mona saying that you don't sometimes have the data, but we've got enough resources to put, capture a lot of data. So what we do then is you train AI models to start to pick up signatures, not just of what you think causes a problem, but what you don't know causes a problem. And then that starts to create these profiles of these are the signatures. And actually, what ends up happening is that, like at the moment, if there was an event, if there was going to be a thermal event, before the thermal event, you will start to see temperature rises. But once you see really critical temperature rises, it's already too late. For many years, we were using then off-gassing, so starting to sniff a particular types of gases that are released during thermal runaway events, and that gave you a time of 11 to 20-ish minutes to react. Now with AI models, you can start to pick up signatures much more earlier and then actually take some effect, right? So in the O&M period, you can go and say, look, there is a defective pack there, remove the pack and then just send it back to the lab and put something else in. So this is now improving dramatically the safety benefits and how safe a system is, to the extent actually that when we present this to insurance companies, we are finding that they react positively to it. So that actually is a very valuable commercial direct benefit by being able to adopt AI like this. Yeah.
Super. Thanks all panelists for presenting. I know we have a lot of additional questions here in the chat, but I don't think we're already out of time. So just sharing my screen again. Again, thanking all the panelists for their presentation. and a really good knowledgeable discussion here. I think it's going to be very useful for students to understand and go through this video. I think upcoming events in this particular set of the activities we have is we have a hackathon planned in IIT BHU in April. Then we will have a industrial stakeholder engagement in Kolkata in April again. And we have a student competition in UK around June timeframe 2026. So we are looking forward for all of these activities. Students who have joined here, please feel free to participate. We really recommend you to participate. Also, we are going to post videos of all these sessions. So if you can go and look at those videos anytime once those are posted. For the feedback, please take the QR code and please provide us the feedback of this particular webinar. Again, thank Dr. Kutub, Dr. Mona for being here and presenting their stuff. Thank you.
Thank you.
Thanks, guys. Bye-bye.
Oh, thank you.
Thank you, everyone.
Thank you, everyone.